It's not fully positive or fully negative because they are not ions and they're not fully transferring their electrons. They are covalent, they're sharing their electrons, but they're acquiring this slight positive or slight negative charge. So what we would do is we would say, okay, chlorine being more electronegative, right, based on our periodic trends, chlorine would acquire a partial negative charge and hydrogen would have a partial positive charge. Meaning that there is a pull of electrons, right? Again, think of it kind of like a tug of war. There's a pull of electrons towards that chlorine. And what we use here, guys, is an arrow with a tail. And that is called a dipole. A dipole really just shows you where the electrons are being pulled. If neither atom is pulling greater than the other atom, then there would be no dipole, and therefore it would be nonpolar because those atoms are pulling equally, or in other words, right, that bond, those electrons are being shared equally. In our example of HCl, however, what we see happen is that there's an overall pull of electrons because chlorine is more electronegative. So what's going to happen is those two electrons being shared, they're still being shared, but chlorine is going to pull them closer to it. And therefore they're shared unequally, or a polar covalent bond. So we're getting just a little bit more specific in the type of bond that's happening. If we actually looked at a kind of an image of what a polar covalent bond looks like, it would look something like this for HCl. If we kind of looked at electron densities, where we would have hydrogen and chlorine, and the larger kind of the bubble around an atom just means it has a higher electron density, which just means it's pulling the electrons right closer to that chlorine. So this would be an example of a polar molecule and a polar bond, and we'll differentiate the two here in a second. Okay, now that's really kind of the nitty-gritty of polarity. How electrons are being shared. Are they being shared equally, or are they being shared unequally? Nonpolar versus polar. We can also look at this quantitatively. I'm not going to spend a whole lot of time on this just because it's not super important. However, this is like why we have ionic versus covalent, but we have electronegativity differences. So you might be given a periodic table with electronegativity values. Every atom, for the most part, has an electronegativity value. The higher that value, the more electronegative it is, or the greater its ability to attract electrons to itself. Again, those electronegativity values increase as you move up and to the right. So as you move up, it gets into that 3-4.0 range. And over here, it's kind of that 0 to 1 range, roughly. What we're looking at is the difference. So think math, right? Think electronegativity difference is just subtracting the two electronegativity values. If that difference is somewhere in the range, and this is, guys, there's a little bit of gray area. If it's somewhere in the range of 0 to 0.4, it's considered nonpolar covalent. Or in other words, neither atom is more electronegative than the other, right? Let's say I have one atom with an electronegativity value of 3.6 and the other of 3.5. Well, that difference, right, is 0.1, which would fall in this range. Neither is stronger in our tug of war scenario, so neither one is attracting electrons better, meaning those two electrons, right, if we go back here to our tug of war, those electrons are really not going anywhere and they're staying in the center, if you will, right? So they're being shared equally, or it's a nonpolar covalent bond. Anywhere of that difference between 0.4 and 1.0, now it's moderately polar now. Now we have a slight electronegativity difference, or it's polar because they're being shared unequally. Anything in that 1 to 2 range is very polar, and anything greater than 2 is generally considered ionic, right? So let's say for a second we had lithium fluoride, so LiF. I don't know the values off the top of my head, but fluorine has an electronegativity value somewhere around 4. I would bet lithium has a value somewhere in the range of 1. So 4, right, our difference minus 1 gives us a value of 3, which is, again, greater than 2, so it would be considered ionic. That's actually why we see these. Okay, are they sharing their electrons, or now, there's such a large electronegativity difference that they're now actually just transferring their electrons and forming ions? Again, here, these atoms are still sharing their electrons. We're just looking at how they're sharing those electrons. All right? So let's talk about bond polarity versus molecular polarity. They're similar, but they're a little bit different. So bond polarity is looking at just the bond. So let's look at carbon dioxide. The Lewis structure for carbon dioxide looks like this. Okay, so in bond polarity, what we're really looking at is one particular bond. We're looking at the actual bond, so a carbon and oxygen bond, or we would look at this carbon and oxygen bond. That's bond polarity, pretty self-explanatory. Molecular polarity is now you're looking at the whole molecule. Okay, so in other words, you're looking at this you're looking at the big picture, if you will. That's the difference. Bond polarity, you're just looking at the bond itself. In molecular polarity, you're looking at the entire molecule. They're very much related, but there's a little bit, there's some differences. Now let me also asterisk this by saying that you can have different bond and molecular polarity. One might be polar and the other might be nonpolar. So we kind of got to pay attention. Now, there's kind of two tricks that I like to reference here. The first one is symmetry. So symmetry, if something is symmetrical or equal on both sides, and here we actually have to take into account the geometry of that particular atom, or if it's not. So let's break this down, and I'm gonna move this kind of over here. So let's put it this way. If a molecule is symmetrical, so we'll say is symmetrical, it is a non-polar molecule. So if the molecule is symmetrical, it's a non-polar molecule. If it is, and I'm just going to put not symmetrical, then it's a polar molecule. So I would make sure I know that. Again, this is to help us identify molecular polarity. The second one is there a net dipole? So a net dipole is really just saying, okay, can I look at the individual bond polarities and can I generalize where those electrons are being pulled? If I can't, then there is no net dipole. And I'll go through this in some future examples, so you'll see exactly how I go about doing this. If there is a net dipole, then it's polar because they're not being distributed or shared equally throughout the entire molecule. If they're not, if there is no net dipole, then it's nonpolar covalent. So let me just put this, and I'll show you what this looks like. So no net dipole means nonpolar. And if there is a net dipole, then it is considered polar. And I'll go through exactly what this looks like in a few examples coming up. So those are really two ways. If you're not sure on one, try the other. So bond polarity versus molecular polarity. Be careful what you're being asked about. So our first example, it says identify the bond and molecular polarity of water. Now you'll see, guys, that again, everything in chemistry builds on itself. We first have to identify, okay, what's the formula of water? Well, we should know this one. What is the Lewis structure of water, the molecular geometry of water, and now we're adding another layer to this with polarity. So first of all, water. And again, if you need help with Lewis structures, go check out one of my previous videos. We're going to put our formula, H2O. So our fewest goes in the center, and we've got hydrogen and hydrogen. Our inventory of our valence electrons, we've got 6 plus 2 hydrogens times our 1 valence electron for each. So we've got 8 electrons to work with. We're going to connect each of those with a single covalent bond, which again represents a shared pair of electrons. So we just use 2, 4, and we are down to 4. Hydrogen is stable with 2, hydrogen is stable with 2, oxygen has 4 electrons around it, once 8, so we need 4 more around that oxygen in pairs like so. So looking at this, I would caution you to first, or after this, to identify the molecular geometry of water. Now, if you remember back to a previous video, we said water's a little bit tricky because again, two-dimensionally, it appears that water is linear. Right? It appears that yes, let me get this. If I have my center atom, my oxygen, and we have our hydrogens right here, it appears that, okay, I've got a lone pair here and a lone pair here. According to the Vesper theory, right, all of those electron dense regions are repelling each other as much as they can. But we forget that it actually exists three-dimensionally, right? We have to take into account the z-axis. So what happens is we have our 2 hydrogens, but remember that this molecule reorients itself, so we have a lone pair here and a lone pair here, and those are all 4 points of repulsion. So water actually achieves this shape, which is bent. So I would encourage you to redraw the Lewis structure of water like so, knowing that it is bent. The geometry is bent. Okay, so with that in mind, let's look at polarity. Now, first, let's look at the bond polarity. So for bond polarity, we're just going to look at one of those oxygen-hydrogen bonds. And really all you have to ask yourself is one more electronegative than the other? Can we look at values, quantitative number values? Yes, but more often than not, we don't really need to. We should hopefully be able to tell that oxygen is way more electronegative than hydrogen. It wants to gain 2 electrons. It really wants to attract electrons to itself, meaning it's more electronegative. So what this means is oxygen would acquire our partial negative charge, meaning, right, it's more electronegative. It wants to attract more electrons to it, meaning if it attracts more electrons, it's attracting more negative particles, right? So it's becoming partially negative, leaving hydrogen partially positive. And from there, we can look at a overall net, we can look at our dipole. Our dipole shows where those electrons are going. A hint to you, a pro tip is your dipole points in the direction of your partial negative. Okay, because if you look at this, right, your dipole shows you where those electrons are going, which is where the partial negative is. So we would draw our dipole like so, showing that oxygen is taking more of those electrons. Then we're going to now look at the next bond. The next bond is still an oxygen-hydrogen bond. Oxygen is still more electronegative, meaning it gets a partial negative, and then this hydrogen is a partial positive. So notice we're looking through this kind of in chunks or in pieces. We would then point our dipole at the oxygen, showing that in that bond, the oxygen is pulling more of those electrons. So what we would say here is the bond polarity, and I'm just going to write bond polarity. Hopefully you're seeing, right, if there is a dipole, guys, that means that it is polar. If there's a dipole, it's polar because those electrons are being shared unequally. In other words, here, oxygen is stealing more of those electrons in that bond. Oxygen is stealing more of those electrons in that bond, right? You'll notice that there's a tail at the end. That's just where like it looks kind of like a plus sign because that's the partial positive. So the bond polarity in water is polar. So the bond polarity is polar for water. We would say it's a polar covalent bond. All right. Now for molecular polarity,